Welcome to the course on computer design of electrical machines. Myself, Bhim Singh, Department of Electrical Energy. So, we like to have today lecture 14, design of three-phase induction machine part 3. Well, we like to, of course, the outline of today's presentation is starting from introduction. We like to talk about computer design example as an analytical approach with it. And then we like to talk about design workflow on induction motor design. Then we like to introduce the computer aided design of induction motor by using both the approach. There are a couple of approaches like analysis method and synthesis method. Then of course we like to talk about the optimal design of these, especially the induction machine in general, and then of course we like to take a case study of optimization, followed by of course the tutorials and some of the problems and examples with the references like. So coming to typically a complete induction motor design case history as an analytical or an example, which consists of many parts. So this is typical example 1 as a case study. Design a 3-phase 50 kilowatt 440 volt 50 or 6 pole squirrel cage induction motor with complete stator and rotor design. Justify with the performance and assume suitable and justified value for design data. So starting as a part 1 of the solution, first we like to talk about the main dimensions of the stator frame. Of course, for that we have output equation C0 equal to 11 B average into Q into cos phi eta kW into 10 power 3. This is the output coefficient where B average is, we call it like a typically the specific magnetic loading normally is in Tesla. So here we are going to select it value, practical value of around 0.5 Tesla. Then we have a specific electric loading normally denoted by Q or small AC. That's we like to specify in a typical range which start from 15,000 to 40,000. So we like to take here a medium value of 28,000 ampere per meter. Of course, the full load power factor, which is the specification of the motor, we like to take power factor 0.87, and then full load efficiency, of course, which also vary within certain range. But here for this motor of typically of 50 kilowatt, we like to take it as a starting point as a 0.89 or 89% efficiency. Of course, the winding factor, which depends on the distribution of winding as well as the pitch factor, how much pitch you are putting for the really particular coil of the winding. So those factors are multiplied and we get the winding factor. Here we are considering with the, of course, the winding factor around 0.955, which is applicable for with the, you can call it 60-degree phase spread with double winding. So coming to this calculation of output coefficient, which you already talked about, 11 B average Q into cos phi eta into kW into 10 power minus 3. So it comes like 114, and then we have a synchronous speed in, of course, in RPS 2F upon P, or in RPM it is 120 F by P. So it's a, because frequency is 50 Hz and number of poles in this machine are 6, so it's a 2 into 50 by 6. So it comes 16.67 revolution per second. So now coming to output equation of the motor, that's Q in kVA, C0 D square L N, where D is the diameter at the air gap, L is the stack length of the machine. So from, of course, from this equation we can find out one relation D square L, which is Q upon C0 N0. Putting the value, it comes 0.0263 meter cube, because the dimension of D square L is in meter cube. So coming to, of course, another relation, this is one relation between D and L, stack length, and the main dimension stack length and diameter at the air gap. So for another relation we have to find out by some other way. So one, of course, one of the way, there may be many criteria, but one of the way the for best power factor operation over the large experience is D equal to 0.135 P under root L. So putting the value of P as a number of poles and L is the stack length. So we can say the relation, this comes as the second relation between D and L. So now from this relation and the previous relation of output equation, we get the D value equal to 0.36 meter or 36 centimeter, L equal to 0.2 meter or 20 centimeter. Of course, from which we can find out the pole pitch tau, that is pi D upon P, it comes 0.188 meter or 18.8 centimeter. Now considering with the two ventilating ducts for such, it also depends that how many ventilating ducts, it depends on stack length. So normally for each 10 centimeter we have one ventilating duct. So here the stack length is around typically around 20 centimeter. So we have a a couple of ducts here. So net length, of course, of the ferromagnetic material in the core, as a L cross we call it L minus NdWd, where WD is the, you can call it width of the duct. So it comes, I mean the net, you can call it the sphere core length comes as a 0.18 meter or 18 centimeter. So considering a stacking factor of 0.92, this stacking factor also depends on many, that what is the thickness of the lamination, I mean like, and what kind of the, you can call it the kind of insulation we are providing on the typically of your laminations of the ferromagnetic material which you are using for typically designing or manufacturing this induction motor. So now taking that factor, we can call it the effective iron length in or stack length is Li equal to Ki into L net, and comes 09.2, putting the value of Ki and into typically the net spherical length 0.18. So it comes equal to 0.166, that's a 16.6 meter. So that's a really effective ferromagnetic material length in the stator, typically of the stack length wise, like, or parallel to the shaft. Now coming to the peripheral speed, this is also one of the important parameter here, pi dr ns, because that's corresponding to rotation of the rotor, and we consider, of course, the air gap is very small, so we consider this rotor diameter very close to the air gap diameter, so it comes pi d into ns, and keeping the value or substituting the value of this, it comes like as a 18.85 centimeter. So now coming to typically of design of stator winding, we say stator winding assumed to be double layer, which I already mentioned, and the motor is delta connected. So motor is provided normally. Why we have to keep such large rating, like around the rating which is we have considered, we take it the motor we normally use as a star delta starter. So at starting we keep in a star, later on we convert into delta. Well, now finding out the turns in case of stator winding, the turns per phase, we can consider the induced EMF is very close to the applied voltage at for rated frequency of 50 Hz. So we can say the induced EMF also equal to terminal voltage, line voltage, that is EPH equal to 440 volt, because it's delta connected. So line voltage equal to phase voltage when it goes to the delta connection. Now coming to flux per pole 5, that comes the B average into pi dl upon P, that is B average into tau. So putting the value of these, it comes 0.0189 Weber. And now from this we can find out number of turns per phase, TPH equal to EPH, that's the voltage applied, divided by 4.44 F kW into phi. So putting the value, it comes 110 turns with the proper rounding up like. So now number of stator slot that we have to select next. So considering the effect of number of slots on phase reactance, the weight and cost of the machine, the number of slot per pole per phase, assume in this case as 3, but normally we don't go less than 2 and we don't go very high also, provided the machine rating is very large and we have a large diameter of the machine. So usually it's order of otherwise 2 to 5. So from which we, for this kind of machine of medium rating, we just consider this as a slot per pole per phase order of the 3. Now, of course, from this we can find out the total number of the slots. So since this total number of slots of stator will be number of phases, number of poles, and slot per pole per phase. So here it is, all the parameters are there, like number of phases are 3 in the motor, and number of poles are 6, and slot per pole per phase is 3 we have considered. So it comes like a 54 slot for this machine on the stator. Now coming to calculating stator slot pitch, that is tau SS, that is pi d, that's the whole diameter at typically on stator side, inner diameter, divided by SS, number of slots. So keeping the value, it comes 0.021 meter. When that decide typically how much is the really the space we can keep of this of one slot, which means it includes the one teeth as well as the slot space area. So now coming to number of conductor per phase, T conductor will be 6 TS upon M, but so keeping this value, we already got a number of turns, like, because we are converting into the conductors and then going by M number of phases, so it comes 220, and then the number of conductor per slot, we can keep the value in this T slot equal to T conductor divided by SS upon M, it comes typically around 12 conductor per slot. That gives the idea of the winding design in the slot line. So now coming to revised number of conductor per phase, because it's like integer concept we have to provide for the conductor, so it will T conductor dash will be T slot upon SS upon M, so that it should be integer multiplied. So that comes around because we have round of number of conductor per slot, that has to be also integer. So 12 into 18, it comes to 16. So now revised number of turns per phase will be T phase dash equal to conductor by 2. It is 216 by 2, that comes 108 number of turns typically in one phase. So now coming to revised value of flux per pole, because this is the design is a iterative method and some of the parameters are really depends on the geometry and logic. So because of this we have to really come out as an integer conductor and all that. So we have to revise flux also. E phase your number of turns are revised. So E phase divided by 4.44 FKW into T pH dash, putting the value it comes 0.0192 Weber, and the size of the conductor, which we are using for the winding of the stator. So that we have to find out depends on the current. So first we have to find out the input power, from which we can find out the input current, full load current. So P input is P output divided by efficiency. So we are designing this machine, of course, for motor for 50 kilowatt, and efficiency we have considered initially 0.89 or 89%. So the power comes 56.2 kilowatt. And now coming to full load current per phase, IS we can call it on stator, which drawn from the supply by this motor. So power divided by M into EPH and P power factor. So it comes like a putting this value of power and the other parameters come 37 ampere. That is the full load current of the motor drawn from the supply, typically per phase. Of course, the line current will be √3 times, because that's a typically you can call it your delta connected one. So current density usually we assume, so here we are considering it at 4.2 ampere per millimeter square, but of course it depends on many parameters like cooling as well as the material property, and of course it decides the temperature rise as well as resistance of the winding. So there are many factors, but the typical value start from 3 to it goes as high as like a 12. But this is nominal with the air cooled, so normally we consider around 0.42 ampere per millimeter. So now cross section of the conductor we can find out AS equal to 37, that is ampere. Rated current in the typically of the winding divided by this current density, so it comes 8.81 millimeter square of the conductor cross section is used for stator winding. Now once we know this, so we have to find out nearby size of the conductor according to the typically thickness and typically of thickness of the conductor as well as width of the conductor, and from this of both cross section area, because they are also these all conductors are also standardized as given in the table. They according to the standard, typically for rectangular conductor, for the copper conductor. So it comes typically from thickness as well as from width. It comes to nearby that area, which we find out little slightly above than that what is 8.81 millimeter square, because less than this is 8.119 and higher than it is typically more than this. So we can select this typically of 9.04, typically cross section area with the width thickness of 1.9 millimeter and the width of 5.5 millimeter. So standard reactor conductor selected here, is dimensions is equal to W conductor and T conductor. So multiplying this 5.5 millimeter into 1.7 millimeter, it comes cross section area of the conductor comes AC equal to 9.04 millimeter square in place of your 8.81 what we found out in previous slide. The size of the conductor with the insulation, we have a insulation over it, so it comes typically in place of 5.5 it goes to 6 millimeter, and in place of 1.7 it goes to 2.2, because we have a 0.5 thickness insulation over it on both side. So now coming to typically a size of the stator slot, as you can see that the winding is 2 layers with several conductor in the slot. As we mentioned, 12 conductor in the one slot. So we have a 6 conductor in upper layer and 6 conductor in lower layer. So 12 conductors in each slot arranged in double layer with the 6 conductor in each layer, and 6 conductor each layer are arranged 3 width side and 2 depth side with the above arrangement, and width and depth of the slots are as. The width of the slot will be space occupied by the conductor, that is typically 3 into, because there are 3 conductor into width of the conductor, so 3 into 2.2 with the physical dimension including the insulation, so it comes 6.6 millimeter. And slot lining, of course we have to put 2 slot lining, it comes like a 2 into 3 slot lining, it's a 2 into 0.8, 1.6 millimeter, and stack length is slackness is 1.8 millimeter. So width of the slot will be W slot equal to 3 times, because there are 3 conductor with 5, 3 conductor plus 2 slot lining plus slackness. So it comes keeping the value of typically of all these parameters, come 10 millimeter. Now coming to typically depth of the slot, because we are, as a depth wise we have a typically 4 layer. So space occupied for the conductor is 4 into the typically thickness into T conductor. So that come 4 into 6, that come 24 millimeter. And slot lining here is, of course, you have a 3 slot lining, so it's a 3, so it comes 3 into 0.8, that's a 2.4 millimeter. And insulation between layers is 1.0 millimeter. So wedge, H wedge, that is a 4 millimeter, and LIP lip corresponding to is HIP is 1 millimeter. So slackness around 2.6 millimeter. So depth of the slot will be 4 into T conductor plus 3 slot line plus insulation plus H wedge plus H lip plus slackness. So putting all value, it comes 35 millimeter. So here the size of the slot comes as a kind of rectangular slot into 10 millimeter into 35 millimeter. Now coming to typically now flux density in stud teeth, because that's also becomes very important design criteria to avoid the excessive scissoration of the teeth. So we consider the diameter at 1/3 height from the narrow end of the teeth, which we already considered in the last few lectures. D dash equal to D plus 1/3 ST into 2. So it comes putting a value 0.383 millimeter, 0.383 meter, and slot pitch at above section T dash SS is a pi D dash upon SS. So keeping the value, it comes 0.022 millimeter meter virtually. So width of the teeth of the at this section will be BS TS dash equal to TS dash minus BB. So putting the value, it comes 0.012 meter, and number of the teeth under one pole is SSP upon P 54/6. So it comes 9 slots under a one pole pitch for all 3 phases. And the minimum flux density in stud teeth BST equal to 5 upon BST dash into Li into SS by P. That's a number of poles per in one, you can call it phase. So from this putting a value, it comes 1.07 Tesla in the stud teeth. And maximum flux density, usually the teeth is 1.5 times of this typical average flux density. So it comes typically 1.61 Tesla, which is well within the stipulated value of less than 1.8 Tesla. Then we come to part F, that resistance of stator winding. So mean turn length of the mean turn is equal to LMT equal to 12 plus 2.3 tau P plus 0.24. So keeping the value, it comes 1.072 meter. And now resistance of the winding per phase of stator winding is RS equal to rho CU. That's a winding is made with the copper. So there is a resistivity of copper. LMT mean turn length of the one turn and into number of turns TPS divided by ACU. That is a conductor cross section area of typically in case of stator winding. Putting the value, it comes to 0.27 ohm. Now coming to for the calculation of stator copper losses as G part. So total stator copper losses, there is a 3-phase winding. So 3 into IS is current to RS. So keeping the value of typically current and resistance, it comes for 1108 watt. Now coming to typically depth of stator core. So flux in stator core usually is half of the per pole, because this half the flux goes one side, half goes into another side of the stator core. So phi SC is equal to half of the pi pole. So keeping the value, it comes 0.0096 Weber. And suitable value of flux density in stator core, usually we take 1.2 to 1.4 Tesla, considering here in between PS equal to 1.35 Tesla. So sectional area of the stator core will be, that's called AC, phi SC upon PSC. It comes putting the value 0.0071 meter square. Now we can find out the depth of stator core from this. So the DCS AC upon Li. So keeping a value, it comes 0.043 meter. And now coming to length of air gap, LG equal to the well tested empirical relation 0.2 plus 2 under root D into L in millimeter. When D and L are in meter, it comes 0.64 millimeter. And this normally we keep lesser than this air gap. This is just guideline. I mean, for modern motor can accommodate much smaller air gaps like. So we keep lesser than that, depends on mechanical tolerance and other factors. So this keeping a large air gap give a penalty on higher magnetizing current. Of course, there are constraints on other side also on both sides. So we normally select little lesser than that, maybe in order of 0.5 millimeter out of that. Now coming to design of cage rotor or rotor. So number of rotor slots. The number of rotor slots are selected based on the following a criteria. There are many criteria just to avoid the clogging. The difference of stator and rotor slots will not be equal to typically. So there is a restrictions on that. This will not be 0 or this will not be equal to. So typically number of pole pair. So to avoid the locking torque, so stator slots will not be equal to rotor slot, and to avoid the synchronous curve, the difference between stator and slot will not be plus minus 6 or 12 or 30, and to avoid the noisy operation, the difference of stator and rotor slots will not be plus minus 1 or 2 or number of poles plus minus 1. So considering all the above factors, the rotor slot comes about as a right selection about 45, and rotor slot per pole will be now typically this rotor slot divided by number of poles 45 by 6, because poles are 6. Whatever the number of poles on stator rotor get dictated by the same number of the poles in the rotor also. So it comes around 7.5. Now coming to diameter of the rotor, so outer diameter of the rotor is dr equal to dl minus 2lg, 2 air gap, and putting the value it comes 0.358 meter, and rotor slot pitch tau r is pi dr upon ss, so putting the value it comes 0.0025 meters. Now coming to rotor bar current, so equivalent rotor current usually is taken 85% of your stator current, so it's IR dash equal to 0.8537, that comes 31.5, and number of conductor stator slots, typically we take ZS on stator side like 12, so number of rotor conductor 1. So putting from this equivalent MMF of 85%, we can say IB, if we keep in this formula, it comes typically order of the current of bar current comes 433 ampere. Now coming to the size of the bar, assuming the current density of rotor bar order of 6 ampere per millimeter square, the reason we consider this as a higher, because the cooling, because of the rotor movement or rotation of the rotor, cooling is better of the rotor. So compared to stator, we take higher current density, and here we are selecting 6, where stator we consider 4.2 ampere per millimeter square. So proving this, from this we can get a cross sectional area of rotor bar AR equal to IB upon JB. So putting value it comes 72.2 millimeter square. So standard size of the rotor bar fusion is WBR into PR at 12 into 6. So from the typically winding, and section area of the typically standard conductor is typically comes from this AR equal to 71.1 if we consider those dimensions like. Now coming to size of rotor slot, upper slot to accommodate the rotor bar of our size is taken as 12.5 millimeter TR and 6.5 millimeter BR. Now coming to calculation of the resistance of the rotor bar, assuming an allowance of 5 millimeter for screwing the rotor bar and for the distance between the ends of rotor core and endings, so length of rotor bar equal to L bar equal to L plus allowances. So putting values, it comes to 0.25 meter, and resistance of the rotor bar RB equal to rho Cu, that's the current density, resistivity of the copper. We are using copper as a bar material here, L bar upon A bar, and putting value it comes 0.074 into 10 power minus 3 ohm. Now losses in the rotor bar will be total copper loss in the rotor bar, NR into IB square RB. So putting the value it comes 625 watt. And now calculating the end ring current I equal to number of rotor bar per pole divided by pi into IB, that's for calculating the average. So it comes typically 1033 ampere. Now finding typically the resistance, for finding the resistance of end ring, we have to again we select almost the same current density as we consider for bar, that is 6 ampere per millimeter square. So area of the end ring is A equal to I upon J as 1033 divided by 6, that's 172 millimeter square. So mean diameter of the end ring may be approximately 5 centimeter less than dr, and mean diameter of end ring will be dm equal to dr minus 0.05 centimeter, that comes about 0.31 meter or 31 centimeter. So mean length of the current path through the end ring will be L equal to pi dm, that is putting value it comes 0.974 meter, and resistance of end ring will be rho R equal to rho LU LE upon AE. So putting the value it comes around 0.119 into 10 power minus 3 ohm. Now the total copper loss in the end rings will be 2, because there are 2 end rings on both the side, 2 I square RE. So putting the value it comes 254 watt, and equivalent rotor resistance rotor copper loss we can find out number of rotor bar NR IB square RB plus 2 I square RE, putting value it comes 879 watt, and equivalent resistance of the rotor is the rotor copper loss divided by 3 into IR square. So it comes typically 0.29 ohm. So flux density in rotor teeth, that is diameter at 1/3 height from the narrow end, we can say of the teeth dr dash equal to TR minus 2 into 2 by 3 STR, and putting value it comes 0.338 meter. Now coming for the flux density in the rotor teeth, the slot pitch at this teeth is TOR dash equal to pi dr dash upon SR equal to, if putting the value it comes 0.0236 meter, and width of the teeth at this section is PTR dash equal to TR dash minus BR, and keeping the value it comes 0.00171 meter, and area of rotor teeth per pole it here T equal to BTR dash into Li into SR upon P, so it comes around 0.0212 millimeter, typically meter square, and average flux density in the rotor teeth will be TR equal to pi pole upon A RT, giving the value it comes 0.91 Tesla, that is typically well below. And now maximum rotor tooth flux density will be 1.5 times of this, with average flux density it comes 1.36 Tesla, that is well below 1.8 Tesla we normally consider it. Now coming to calculation of depth of the rotor core, so flux density in rotor core, again we call it BRC, so we normally keep the value between 1.2 to 1.4 Tesla, so here we are selecting 1.35 Tesla. So flux in the rotor core will be pi r equal to, again half goes to the one side, another half the half pi pole, and keeping this it comes flux comes on in core. Rotor core is 0.0096 Weber, and sectional area of the rotor core will be ARC equal to phi RC upon BRC. So it comes typically value 0.0071, and the depth of the rotor core DCR ICR upon Li, so it comes 0.043 meter. Now coming to, these are the typically dimension we got it. Now we have to calculate the typically the performance of this machine. So how we can get a performance? First we like to estimate the iron losses A part. So losses are quite negligible in rotor teeth and rotor core. So because of extremely low rotor frequency, because the rotor frequency is slip frequency, and slip is order of 4 to 5%. So here the frequency comes 2 to 3 Hz, which produces almost negligible core losses in the rotor core and rotor teeth. So we consider normally only stereo core and stereo teeth where the frequency is a part of rated frequency, that's around 50 Hz in the case what we are considering here as a design. So as such, these are only calculated for stereo teeth and stereo core, and stereo means stampings of low steel and 0.5 millimeter thickness. As you can see, loss watt per kg, characteristic of the material of this steel, and it's a different certainly for thinner laminations of 0.54 mm, it is much lower and compared to 0.5 mm. Normally for rotating machine we keep the thickness of 0.5 mm, especially other than for special design, and you can see how the core loss per watt, typically iron loss per kg varies here typically. So for different flux density, because in different parts of the machine are the different flux density like we calculated. The flux density stereo teeth, rotor teeth are different, and flux density stereo core and rotor core are different. So we have to use the entire characteristic because flux density varies here. So coming to first as iron loss in the stereo teeth, the volume of all the teeth will be area of one teeth multiplied the height of the teeth into, that's a volume, into the number of teeth, that is SS number of stereo slot. So keeping the value it comes like 3.768 into 10 power minus 3 meter cube, and weight of all the teeth, this volume of the teeth multiplied the density of the steel. So keeping the value it comes 29.4 kg, and maximum flux density in the stereo teeth is 1.61 Tesla, which we estimated. So corresponding to this characteristic of loss watt per kg, we get a specific iron loss per kg at 1.61 Tesla, P loss equal to 23 watt given here per kg, and total iron loss will be the P L core WT into P loss, that will be 29 to, that's typically the weight 29.4, so it comes 676 watt in typically in stereo teeth. Now coming to iron loss in the stereo core, the sectional area of stereo core already we got it, AC equal to 0.0071 meter square, and mean diameter of the stereo core below the stereo slot is DS equal to D plus 2ST plus T core equal to 0.473 meter. The volume of stereo core will be Vs equal to pi ds into AC. Putting the value it comes 0.0106 meter cube. And the weight of the stereo core Ws equal to Vs into density, that comes around 82 kg. And maximum flux density in stereo core is typically 1.35 Tesla watt we consider it. And iron loss from this characteristic at 1.35 Tesla per kg, per unit kg is 18 watt per kg. So total iron loss will be this, specific loss and multiply the weight. So putting the value of this WSC and P loss, it comes around 1476 watt. So now coming to total no load losses. We say total iron loss is equal to PL core plus PLT. Putting value, it comes to 152 watt, and friction windage loss, PF, normally we consider as a percentage of output power. Considering 1% of output power, it comes to 500 watt. Hence the total losses will be iron loss plus friction windage loss, that comes to 652 watt. And no load current, active no load current will be correspond to this loss component, I mu equal to PNL divided by ampere, so it comes around 2 ampere. And now we have to calculate now magnetizing current to get the total this. So for calculating the magnetizing current, no load amperes needed by various parts of the magnetic circuit are first calculated. So considering the ampere turns for stator core, so the pole pitch as mean diameter of stator core tau CSC pi DSC upon P. So keeping the value, it comes 0.248 meter, and length of flux path in stator core, that is LSC, 1/3 of the TSC, so it comes 0.083 meter, and ampere turns per meter at 1.3 Tesla, it comes ATSC equal to 470 from the magnetization characteristic of this particular material, and total ampere turns of the core will be ATC into LSC, so length of magnetic path and this, so it comes at 39 ampere. Now coming to the ampere turns for stator teeth, ampere turns for flux, average flux density in the stator teeth we already estimated, it comes 1.07 Tesla, and flux density at 30 degree from typically interpolar axis, it comes BT 30, that's 1.36 BST, so it comes 1.46 Tesla, and ampere turns per meter at 1.46 Tesla flux density, from the characteristic of the material as it is shown here, it comes 80 ST equal to 800 ampere per meter, and the length of flux path in stator teeth equal to ST, that's a 0.035 meter. So total ampere turns of stator will be 8 capital AT, SC equal to 80 small st ST into ST. So putting the value, it comes 28 ampere. And ampere, now coming to ampere turns for air gap, which is the major component. So we can say slot opening BSO equal to 4 millimeter, and slot opening oblique air gap is BSO on LG, that is 4 into divided by pi 0.4 is 6.2. Now coming to ampere turns for the air, so we have to calculate the Carter coefficient for this. It comes KOS 0.68 from the characteristic of Carter coefficient with the slot opening, and gap coefficient for stator slot comes Kg S equal to tau S upon tau S minus BS KOS, it comes 1.12. And now we have to consider the slot rotor effect of slot rotor opening for the increasing the effective air gap length, it comes BR0 equal to 2 millimeter, and rotor slot opening upon air gap, it comes 3.1. So Carter coefficient for this factor is a KO0 equal to 0.46, and we can find out now gap coefficient for this equal to KGR equal to tau on tau minus BR, putting a value, it comes by 1.03. The effective length of air gap now come LG dash equal to KGS KGR into LG. So putting all the value, it comes 0.742 millimeter square. Now coming to this width of the ventilating duct or air gap length, WD upon LG, it comes 15.6, and Carter coefficient for because of this duct, it comes for this ratio of 15.6, it comes KV equal to 0.7, and considering the effect of ventilating duct, so we can call it effective axial length is LG dash equal to L minus KV and D with WD, so it comes 0.186 meter, and air gap area per pole, A pole equal to pi D L dash upon P, putting value, it comes 0.035 meter square, and flux density in the air gap, now we can find out B is equal to 5 pole upon A pole, it comes 0.547 Tesla, and gap flux density at 30 degree from pole is 1.36 Bg, it comes 0.744 Tesla. Now ampere turns for air gap now will be equal to ATG, will be equal to 1 divided by 4 to 5 10 to the power minus 10 Bg dash into Lg dash. So putting value, it comes 440 ampere, and ampere turns for rotor teeth, we can calculate here. So average flux density in the rotor is BRT equal to 0.91 Tesla, and flux density rotor at 30 degree from pole center, it comes 1.36 into BRT, it comes 1.24 Tesla, and ampere turns per meter for the core of the rotor teeth is at 1.24 Tesla is 80 small ATR equal to 400, and length of air gap. Length of flux path in rotor teeth is HRT, that is 12.5 millimeter. So total ampere turns for rotor teeth is capital ATRT equal to small ATRT into HRT, giving value it comes 5 ampere. Now coming to the typically ampere turns for rotor core. So average flux density in rotor core is BRC equal to 1.3 Tesla, and ampere turns per meter at 1.3 Tesla from this material what we are using for rotor core. It is a small TRC equal to 470, and mean diameter of rotor core below the slots is TRC equal to DR minus 2H TR into DCR. So this value comes around 0.285 meter, and pole pitch at the mean diameter TRC will be pi DRC upon P, that comes 0.15 meter. So length of the flux path in the rotor core LRC will be 1/3 of this, so it comes by 0.05 meter, and total ampere turns for rotor core is capital ARC small ARC into LRC, it comes 23 ampere. Now since there are 5 parts in the magnetic circuit, so total ampere turns of the magnetic circuit 30 will be stator teeth MMF, ATST, MF required for stator core ATSC, air gap, MF required for air gap ATG, MF required for rotor teeth ATRT, and MF required for rotor core ATRC. Putting all these values, 39 plus 28 plus 440 plus 5 plus 23, it comes 535 ampere turn. Now magnetizing current IM equal to P 8030 divided by 1.17 K omega into TPH. So putting value, it comes 13.3 ampere. So now no load per phase current will be I0 equal to under root I mu square, that is core component, plus this magnetizing component of current IM square, it comes to under root 2 square plus 13.3 square, it comes 13.4 ampere. And no load current as a percentage of full load current I0 upon Is into 100, that 13.4 divided by 37 into 100, it comes 36%. So now no load power factor is I mu upon INL, so it comes 2 upon 13.5, that comes 0.15 as no load power factor, which is usually quite low. Now coming to the calculation as a part of performance as block rotor current. You can call it standard or block current. So we have to find out, of course, all the block rotor condition, what is the current drawn by the motor at rated condition. So we have to find out the parameter, equivalent safety parameter, which comes in the series. Typically we already got the resistance, we have to find out the typically leakage reactance for stator and rotor or combined leakage reactance here. To calculate the block rotor current, the total phase reactance must be determined first. So for equal KNF motor, total reactance is XL equal to XS plus X0 plus XZ. So slot leakage is reactance is XS equal to 15.8 FL lambda in bracket TPH square P upon Pg dash into 10 power 3 ohm. So stator specific slot permeance here lambda HS, which is used here for stator, is H1, of course slot opening of different one, H1 upon 3 BS, H2 BS, and 2H3 B3 plus B0 plus H4 B0 according to slot dimension. So here we have already the slot dimensions, where the width of the stator slot is BS equal to 10 millimeter, stator slot opening is BSO equal to 4 millimeter, and space occupied by the conductor slot, that wise H1 is 24 millimeter, and of course the space in the slot above the conductor and below the wedge is H2 equal to 2 into 0.8 1.6 millimeter. Space occupied by the wedge H3 4 millimeter, space above the wedge lip is H4 equal to 1 millimeter, and putting this all these dimensions in lambda s, that is a permeance slot permeance typical for slot permeance, that comes 1.78. For similarly for rotor spec slot permeance lambda SR is again function S dash upon 3 BR, H2 dash BR, and plus 2 H3 dash BR plus B0 plus H4 dash upon BR0. So here the rotor slot opening BR0 is 2 millimeter, H1 dash B 12 meter, H2 dash, of course considering 0, H3 base D, and H4 dash 0.5. So lambda SR comes after putting this value 0.86. Now for rotor slot permeance coefficient referred to stator, that we have to refer from winding, effective winding also. So winding factor W1 square into S1 upon KWS2 square S2 into lambda. Putting the slot number here and this permeance, it comes 0.94. The specific slot permeance for stator and rotor lambda comes lambda SS plus lambda SR dash, that comes 2.72. Now number of stator slots per phase is already G dash equal to 3. So slot reactance XS putting in the formula 15.8 FL tau TPH square upon P divided PG dash into 10 power minus 3. So putting value, it comes XS equal to 0.633 ohm. Now coming to overhang reactance. The overhang reactance XO0, again an empirical relation well verified, 15.8 F L0 lambda 0 at TPH upon PG dash minus 3. Putting the value, it comes X0 equal to 0.548 ohm, and zigzag reactance XZ equal to 5 by 6 into XM in bracket 1 upon G S square plus G 1 upon G R square. That putting value, it comes XO equal to 0.831 ohm. Now total reactance per phase is XS equal to XS plus X0 plus XZ. Putting value, it comes 2.012 ohm, and where the resistance, total resistance is referred to stator as R1 plus R2 dash. We already got earlier, so it's a 0.27 plus 0.29, it's a 0.56 ohm. So impedance per phase of this induction motor of 50 kilowatt, Z equal to under root R square plus X square, it comes 2.1 ohm, and block rotor current will be now IS equal to V upon Z phase. So per phase voltage 440 divided by this impedance 2.1, it comes 209 ampere, and block rotor current in terms of load current ISC upon IS, it comes 209 upon 30, 5.66, which is normally between 5 to 7 per unit. It's only 5.66 per unit. Block rotor power factor of IC upon R upon Z, so it comes 0.267, which is certainly higher than no load power factor. Now coming to full load efficiency, for that we have to find out the total losses at full load. So total loss is equal to stator loss plus no load losses. So here we already estimated typically these all losses. So putting value, it comes like 4640 watt, and efficiency at full load will be eta equal to PO upon PO plus P loss. That's putting all value here, so it comes 91.5%. We started from 89, so we got 91.5. This is quite optimal, good design. I mean, what we really have gone through. Now considering for calculation of the slip at full load, so rotor input equal to output plus percentage loss plus rotor copper losses. Putting the value, it comes like a 51.38 kilowatt, and percentage will be at full load will rotor copper loss divided by rotor input into 100, so it comes 1.71% as a full load slip. Now coming to starting torque calculation for direct online starting ISC upon IR square is into slip into TFL. So putting the value, it comes 0.76 into TFL, and maximum output is putting value 3 VPH ISC minus I0 divided by 2 in 1 plus cos phi SC into 10 power kilo. It comes 102 kilowatt for a motor of typically of 50 kilowatt output. So these are analytical complete design of this motor. Like now as an example, now coming to as a design workflow of this induction motor design. So before understanding the computer age aspect of the designer needs to break down the design process into multiple subparts, and these parts could be referred as a subroutine or can be solved independently or in the main design workflow. And the following section details a few of these subroutines involved in the design of induction motor, which can be further used in computer design of this induction motor. Like this is a design workflow. If you look into here as a sub process, we start from the design, then we have a sub process 1, where we have a sub process part of subroutine 1 and 2, and sub process 2 we have a subroutine again 1 and 2, and then we have a decision making and go to the end for as a design workflow. So we do the calculation and then we come to revision and followed by the end if all decisions are correctly taken. So example is here. We have a typically an example that performance calculation first sub process involving the subroutine BH curve definition. So due to the design process being long and complicated with many decisive parameters involved, it is usually preferred to be solved in the parts or sub process as shown. Example of free design sub process are given as next. So you can look into how we go ahead to start the process A. Example is performance calculation. Then we go for subroutine and we take a decision A whether it is right or not, and then we go to end. And as a second subroutine, as a part of it as a subroutine A. What is subroutine A? Example is BH curve characteristic calculation with the loss per kg values, what we already done in example, and we then end the subroutine to go back into the main process. Now coming before starting the design process, the scope of design need to be assessed. So what are the parameters like variables? The designer have to have a flexibility to change or choose within certain limits. I mean, because design is a very, you can call it reasonably iterative process because of this, because there is a range of the variables which can be there. Depends on the rating, depends on material property specification also. So what constraint, either design standard, client requirement or specific application requirement need to be considered, and typically can the design be optimized, if then what are the objective to be considered. So considering as a scope of design, we have of course the specification as a starting power, which can be kilowatt or megawatt, especially the for motor. Then we have a operating voltage, starting current, then frequency like 50, example is 50 or 60 hertz. Then we have a rated and maximum speed and torque, and then operating frequency, duty cycle, number of phases may be 3 or multi-phase, or stator winding, that winding turns and gauge, rotor winding turns and gauge, and air gap dimensions, voltage limit for winding, current limit for winding. These are the some of the typical kind of specification and constraint. Now coming to like insulation requirement, like winding layer insulation, insulation between winding, slot insulation, and type of winding. Winding type and sequence may be like integral, fractional, or concentrated winding, and then enclosure and frame size according to the different standard, and type of coupling, shaft design, magnetic or non-magnetic material, type of footings, ambient temperature and temperature rise, any value within the limit according to the class of insulation. Then of course 18 step, like step dimensions and thickness like 0.2 mm to 0.6 mm, usually prefer for rotating machine 0.5 mm, but some specific case we of course take as a lower than that as a 0.35 mm or so. Then stack material, like typical example is M series steel, cobalt steel, etc. Then bar material may be copper or aluminum, like, and type of die cast is maybe aluminum or copper or aluminum copper alloy. Now coming to flux density, designer choice is for computer selection, like rotor, core and slot, what the flux density we have to consider, and stator, core and slot, and then typically the air gap. Now coming to the just on the second point, mode of design, it can be computer design like a synthesis or automated process, or manual design like analysis method, or it may be size directed design like a hybrid of the two. I mean, the analysis means we are using computer only for calculation but taking a decision manually, and synthesis approach means we are doing calculation as well as giving the decision also to the typically to the computer to take final decision. And of course another is the hybrid method, in which we do typically combination of both. So now considering as a variables, the variables of induction motor design could be like a machine dimension, like stator dimensions, air gap dimensions, and rotor dimension, and material choice, typically which material, and selection of average flux density in the air gap, slot and core of stator, and slot and core of the rotor. Then the selection of electric loading is small AC, type of winding and turns, and stator and rotor skew angle theta and linked to resistance, and stack length to pole pitch ratio selection, L upon torque, current density selection as linked to the ventilating and cooling, type of cooling, and the rotor slot depth to rotor width ratio, aspect net resistance starting performance, because decide the leakage reactance as well as the resistance, ending dimensions like depth to width ratio, but that decides also the resistance here as well as, and the cooling and ventilation corresponding to the temperature rise of the machines, and how good the ventilation depends on the speed also at which the motor is running like. So these are some factors. Now coming to as a objective, if we say that we want to optimize the design or to get some objective, so some of the objective function in the induction motor design could be like minimize the overall cost, including the cost of material, labor cost, and losses, and maximize. Another objective may be maximizing efficiency, power output, etc. for a given frame, and could be single objective or multi-objective as a combination of part of many objective with proper weighting factors like. Now coming to constraint, there are constraints for the induction motor design, which can be resistance constraint or resistance leakage, possible flux density for that particular metal because of saturation limit, and physical dimension of the machine and winding because of the frame size. The induction motor design is constraint design problem. So now as an example, how the flow chart is there for design of stator, we start with input data like a power rating, voltage, number of poles, frequency, speed, efficiency, power factor, average specific magnetic loading B average, specific electric load AC, rotor speed, and winding factors. So we calculate kVA input, and we calculate the kVA output coefficient, then determine the synchronous speed, followed by calculate D and L, and we take a calculate whether peripheral speed is within the certain limit for which machine is designed. If no, so then we have to certainly again go for iterative procedure to select a typically a sum of the parameters, especially pregnancy and your specified electric loading and magnetic loading. Now, if yes, the design is acceptable according to peripheral speed, then we go to calculation of stator dimension, determine the stator turns per phase, calculate the stator current per phase, determine the conductor size, calculate the total number of stator slot, stator conductor, determine the air gap length, and then print all the values, then stop. So, this is the flow chart typically on for design of the stator. Similarly, we can have a calculation of main dimensions as a sub process to start with input data power, phase age, frequency, synchronous speed, efficiency, power factor, magnetic loading, electric loading, winding factor, and stacking factor. So, first we calculate the number of poles corresponding to the typically the speed, then we go for KVA calculation from power and efficiency and power factor, then we go calculate output coefficient as given relation here, then we go for aspect ratio, another relation virtually for L upon tau flow, and then calculating D square L, then calculating the diameter and followed by stack length, and then actual stack length, and then stop. So, this is a calculation for main dimension. Then calculation of sub process like starting from input voltage, connection type, and winding factor. We go to calculation of flux, the average L upon into tau, then number of turns, E upon 4.44 F into kW, then the slot per pole per phase, total number of slot, then poles and per phase, calculated, then number of total slots, because this is a like integer value, so it should be multiple, then the slot pitch by D upon SS, then we calculate the number of total turns, then we calculate the conductor per slot, then total number of conductors, then conductor per slot, and the effect, we divide by 6 so that we get the effective number of again turns properly, then calculate the coil span according to pole pitch, then we calculate the pitch factor that is cos pi upon 2 pitch, then distribution factor according to distribution of winding, and then winding factor Kp into Kd. Then of course, we go to calculation of stator current from typically from power, number of phases, efficiency, power factor, and voltage. Then once we know the current, then from considering current density, we calculate current and cross section area of the conductor, then we get the typically slot depth coming from different dimensions, then width of the slot from different dimensions, the slot pitch, width, and tooth pitch, then tooth plug density, because that's a limiting factor, and then the cross section of the core, stator core, then depth of the core, and then stator outside diameter, and we stop. So, this gives the complete dimension of stator to us as a how the workflow is there of the design. Now, coming to the design of the rotor as a flow chart for rotor design, we start from give the design specification, parameters, and constraint. So, we go for typically find the dimensions D and L, determine the air gap length and rotor dimension, then we calculate the determine the typically the slots, rotor bar current, depth of the stator rotor core, and calculate the end ring current, then determine of course the loss in the rotor, typically winding loss in the rotor bar, ending current, and efficiency. Then we go to the typically calculate the slip, then we say whether slip is within the limit or not, then we modify again the plug density and resistance, go back. If yes, then we go for calculation of temperature rise. If temperature rise within the limit according to insulation, then we go print result. If it is not though, then we go again for iterative procedure to bring into the within the limit. So, that's about the rotor design. Now, as a part of typically this process more microscopically with the starts, we have a stator dimension already we calculate from stator design D and L, then we calculate the air gap length from typically from L is equal to 0.2 under root DL, then rotor diameter D minus 2 LG, then rotor bars typically SR equal to SSP by 2, then the rotor plot pitch by SR pi DR upon SSR, then we call it rotor bar current from this relation, then bar cross section area, then we calculate the rotor bar width, then rotor bar depth from these relations, and rotor bar pitch, and then we got the rotor width, and then we go to next to calculate the rotor flux, then rotor bar length, rotor bar resistance, rotor conductor losses, then area of the end ring, depth of the ring, and then typically the diameter at that depth and ending diameters, then ending resistance, then indic conduction of total copper loss or total winding loss in the rotor. Then we calculate the slip from that, full load, typically the full load slip, and then the rotor core depth, and then following the rotor inner diameter, and we stop. So this covers the whole rotor design process. Then we come to the calculation of no load current, as a pseudocode is given here, as we can calculate the from all the Carter coefficient as we already given examples. Okay, then we calculate effective air gap length, then flux density, width, and total virtually the MF required for all the 5 parts of typically of magnetic circuit like stator core, stator teeth, rotor core, rotor teeth, and air gap. That gives the total MF required here to workflow. And then we calculate the typically magnetizing current from this. That's the procedure typically to get. Then we go to the loss component. As we already given an example with the different formula, as you can see here, width and flux density in different part, then core losses in stator core, stator teeth. We consider core loss only in this part, and we calculate your loss component of current typically. Then of course we go for all the equivalents, typically magnetizing current, reactance, and the total resistance. So this is calculation of your block rotor current calculation from all these parameters in these steps like as a code. And then of course we calculate the efficiency. Once we know all the typically the all losses and output power, so this gives efficiency. So this is a you can call it code for the relation what example we have given in this manner like one have. Now coming to as example of a case study of subroutine, typical example we take a curve fitting of magnetization characteristics. So it becomes very important. We have a material property, and this magnetization characteristic is a part like what both as a part of the performance requirement as well as the example of course given here. So objective is curve fitting of magnetization characteristic of typical of induction generator and magnetizing characteristic obtained by H curve of the core material. So we need to derive the air gap flux voltage versus magnetizing reactance, data from air gap magnetizing current, and only a material saturation current need to be assessed properly for getting a accurate performance like. So here the background is BH curve are used to obtain the relation between the current applied virtually in terms of MF and the flux density. And how we estimate, we have a lookup table for the material, and then we go to typically kind of maybe a polynomial equation for the this characterization and use the other mathematical relation for fitting the curve, typically for loss curve as well as BH curve of the machine and learning, and we can use the machine learning kind of based estimation. So we also need to estimate the least computational effort, which needs to that for fitting this curve. So in this process of this curve fitting of the magnetization characteristic, we can start with, and we have a sub process 1 and 2. In sub process we have a subroutine 1 and 2. Similarly, we take decision, and so BH curve estimation can be set as an independent subroutine and used in flux density determination stator teeth, stator core, rotor teeth, rotor core, and we get the magnetization characteristic as well as air gap. So now coming to curve fitting of this characteristic, the generally input is Hx, that is a you can call it the ampere turn meter, and output is the flux density as from this. And the various form of curve fitting used include the polynomial estimation, hyperbolic representation, exponential representation, and 10H representation for this characteristic. And these are the typical example, what kind of characteristic you can take for this magnetization characteristic as a polynomial third degree given here is a typical example of a particular machine, or as a typical example of a relation, nonlinear relation or exponential characteristic, or or another kind of exponential characteristic or tangential characteristic of both. So there are 6 ways how you are presenting virtually this magnetization characteristic with different parameters of these relations for the same particular, and then calculated typically how many points are taken, what is the really RMS error as a percentage here like. So these are the different characteristics how really curve fitting done by different methods. For a typical example for voltage versus magnetizing current as well as voltage versus air gap voltage versus magnetizing reactance, like for using all these typical examples of curve fitting. So that's the way how we can really get these all by different methods the curve fitting of VG versus. So this is another method. So there may be many methods how we really take care of these characteristics into account for material according to metal. Now coming to computer design of the 3-phase induction motor. So as you studied in earlier portion, the approach of the design of electrical machine is broadly classified into 2 categories: analysis method and synthesis method, which given by Rauji in 1959. And for design of induction motor, it means dimensioning the induction machine for a given specification. So by design, we mean the synthesis by calculating the performance for a given geometry is called analysis. What I mean here, Analysis process means we are using the computer for calculation, and synthesis means the calculation as a decision is taken by the computer only. So design means synthesis uses the analytical iteratively, because you have to calculate many times to get the right decision. So as a iterative fashion, analysis implies only using the mathematical model for calculation only. So typical example here, as an analysis method, we start, decision is taken by human, and then we go to input, calculate the performance calculation with the output, and we check whether it is, the human calculate whether right or not. So then it, if yes, then stop, if no, then it goes back. And however in synthesis, we got only final. So we start with the performance specification, then consider the value for variables, design calculation, performance calculation, compare and calculate. If performance is not satisfactory, you have to adjust the variable again back for this, and then again finally calculate total cost and pre-design. So in this is the decision taken by computer itself by logic, but in analysis approach we use only decision by human. But of course both methods have a relative advantage and disadvantage for this electrical machine design. Now coming to analysis method, involve more user input after each step for completion of assessment of one model, while in synthesis this user input can be automated and the mathematical model may be of field distribution like finite element analysis type or circuit type, and as FE models are computationally time prohibitive, so they are in most cases used for performance validation after the design optimization based on analytical models. So the typical example may be covered in the design and optimization of the electrical machines. We start from the design, and design consists like motor type of topology, dimension and material, electromagnetics, calculation, then structure calculation, thermal calculation, inverter conduction, process and design, and then provide the feasible design and information developed to optimization model. Optimization of course use the model for calculation like single or multi-objective, discrete or continuous deterministic robust, and we use the algorithms for optimization like classical numerical algorithm, intelligent algorithm, single or multiple objectives, then discrete or continuous hybrid algorithm, and then others. And of course we have a methodology like surrogate model phase, sequential method, then multi-level, multi-dimensional space mapping and others. And then we go back, offer optimal design with the improvement for calculation or final calculation. So this is the process how we follow in typically in design and optimization of electrical machine. So coming to induction motor design by synthesis method, there have been a lot of literature, because this induction motor is more than typically typically 150-year-old motor. It has gone to many innovation as well as the synthesis method of optimized design. So typical example is here synthetic design pseudo for skull cage innovo. So we start from design input, design specification, parameter and constraint, then we initialize, and while we go in a loop method, we find out all the dimensions of what we give an example like conductor size, slot and current density with the many values, and then constraints, and then we calculate resistance performance parameter as a constraint, then find out main dimensions like D and L, calculate the air gap length and rotor diameter, performance selection of slot, stator teeth, number of stator conductor and winding. In many cases there are not much choices available to, and determine the number of slot, rotor bar, current, depth core, then calculate the entering, determine the copper loss in rotor bar entering and efficiency, and calculate the slip, and if value is within the required, not required, then you have to go iterative. If yes, then find out the temperature rise. If yes, within the limit, then go to AND, otherwise again you have to go for iterative. So that becomes the iterative process as a synthesis. Means decision is taken by the computer in this process, a simplified process, just to explain as an example here. So now in case of slip ring induction motor, the difference is only the rotor. Otherwise similar that we calculate the rotor, typically the windings and calculation of windings like. So now coming to like a typically induction motor designed by other method like a reluctance network method. Typically the magnetic model of the cage induction motor is constructed using a reluctance model, and model describe the cross section of motor, and electric models of the winding of the motor. The magnetic model and the mechanical model of the motor are configured according to figure like for reluctance. So here you can just see how the reluctance motor, we start from supply and then go to electrical model of primary winding, then magnetic circuit model, then we go for mechanical input as well as we go to electrical model as a secondary winding calculations like. So that's about, and how it goes to calculation. This is just like a little bit mix of the lump parameter and the distributed. When the flux path is divided into smaller parts, even the flux region has its own reluctance. So reluctance elements of the region form a chain of elements as a current flux path. And here you can just see the reference flux path, of course, in the typically standard flux path. So radial and circumferential reluctance calculation of the typically of different parts as a relation of in different after a lot of validation of this permeance and calculation. So typically for the different sizes, you can say the radial and circumferential reluctance component of slot region or like calculation of another slot, the third kind of slot. So this is typically the, you can say we have a dimension of the slot of different variety for stator as well as stator slot like. And then you can just have a calculation of, I mean an example how the typically the slots are there starting from yoke portion, then bottom, middle, top and opening, many parts as a network, and then typically getting the characteristic like related to different parts of this MF distribution of with the more detailed configuration with the proper, I mean the much better result like. Similarly, model for stator slot factor of both the typically the motor like. Then the motor road slot pitch factor sector calculation of your single motor. Then similarly for, you can call it double cage rotor, because sometimes double cage rotor are there, as you can see that geometry of this, calculate the reluctance model and electrical model. Now coming to typical example as optimal design of electrical machine. I mean, what is the optimal design? The design of electrical machines consists of two distinct stages, the dimensioning calculation stage and the verification calculation stage. So dimensioning includes the choosing the material, the topology and the calculation of all geometry parameters starting from machine design specification, and because of the relationship between the machine performance indicates the geometrical dimensions and are rather involved or, and they are very highly nonlinear because they are highly buried into the variables. So it is impossible to produce a set of inversion functions or the math or numerical relations to distinguish the latter from the former. So we say the as a performance index Pi equal to a function of typically of the variables where there are number of n variables, I varies from 1 to n like, I mean here as you can see here. So we can say Pi equal to Fi into x. So in general there are more than one variable, I mean vector that satisfy the Pi. Also for some design specification there may be no design solution easy, like a unit power factor may be considered for induction mode. That's not practically possible with the certain types of machine. By classical non-optimal design, a possible X is found to be satisfying the mode. So typically the design of these machines are the constraint design. They cannot be considered as a mathematical simple relation like, I mean also. So there are a lot of constraints. So optimal design is nothing but select the after mastering of a good part of the all feasible variable values, the solution that satisfy a given optimum criteria. Typical example is minimum initial cost, weight or maximum efficiency. As the inverses of functions Fi are not admissible to determine the vector of geometry, the electrical and magnetic stresses are chosen like current density as a variables, current density ampere meter or linear current density ampere per meter, flux density B, shear rotor stress in Newton per meter square based on the past experience, and also some detailed slot geometry parameters such as slot opening at the air gap, slot wedge thickness. They decide a lot of physical, you can call it the physical phenomena in the machine, typically the leakage as well as overload capacity, noise, vibration in the machine. Thus, using the law of electromagnetic and geometrical relationship, all geometrical parameters are calculated, and as the electrical and magnetic stresses have been chosen arbitrarily, there is no guarantee that the geometrical variable vectors X will satisfy the design specification Y, and consequently the verification of performance mandatory as a part of design process. So in general, to fulfill the performance Pi, the dimensioning calculation has to be redone a few times. That's why we call it this design. Optimum design is a iterative procedure. So the geometrical dimensioning is found iteratively even with the classical design. The number of iteration depends on the strategy chosen to choose the electric magnetic stresses after verification, each verification of calculated subroutine. So the reduce the number of iteration, a correlation between the electric magnetic stress changes and geometric parameter variation has to be established as a lookup example as a lookup table. However, the number of iteration remains high except for highly experienced designer who feels the way to design goes. So now coming to typically the stage of a classical design approach are shown in the adjacent figure, and dimensioning and the verification calculation are characterized, and selection of electric and magnetic strengths of initial geometry parameter is still done by the designer. So here typical example for classical design approach is starting from design specification, then choose the electric and magnetic stresses, then go to dimensioning calculation, electromagnetic verification. If it is not, we have to go back to modify the selections of the parameters, and if yes, then we go to thermal verification, temperature rise and other things. If yes, we go ahead, otherwise we go back again to modify the design, and then we check the mechanical verification with the stress and all that. If no, we have to go back. If yes, then we go to elaborate technical document as a design data or design sheet of this machine. Now, if the design specification are to be too restrictive, finding a solution can be either very tedious or even almost impossible. On contrary, for low-level specification machines, configuration of lower cost or good performance may be obtained at same cost. A typical classical approach may be their design, starting from design specification, choose electrical and dimensioning again with the same kind of process what we discussed in previous slide. Now coming to here as a optimum design flow chart, we go to with design specification with minimum specification like as objective function, then electromagnetic stress calculation and initial geometry variable calculation. We go to dimension calculation, then parameter computation, objective function evaluation, then electromagnetic verification. If yes, go ahead. If no, add the penalty to objective function. Then we go thermal verification. If yes, go ahead. If no, then add the penalty term. Then go to mechanical verification. If yes, go straight. If otherwise, add the penalty objective function. And then go to if the objective function is minimum. If yes, go to elaborate design document or design sheet. If no, then you have to go again mechanically to adjust the electromagnetic stresses and geometrical variable to improve the objective function. So this is the process as a, you can call it as an example. We have optimal design flow chart. So coming to the stage of optimal design are shown in the previous slide. So optimal design specification contain in general the minimum performance requirement and objective function, and the initial electromagnetic stresses and geometrical parameter are either specified by the designer or randomly generated through dedicated routine within the specified domain according to standard. So dimensioning and parameter calculation are done in a classical design, but the additionally the objective function is also calculated. Then the electromagnetic, thermal, mechanical verification calculation are performed, and for every performance index there is a that is not suitable, a penalty is added to the objective function to avoid the unaspected design. If the penalty coefficient are high enough, then their requirement will be satisfied in the final design. So coming to optimization case study for design of three-phase induction motor. Now coming to as a induction motor design optimization can be classified under nonlinear inequality and inequality constraint optimization problem. And in this area there are no algorithm or iterative scheme which guarantee that the global optimum, in our case a minimum, will be found, because this is conditional design or constraint design in general. So most of the algorithm proposed in the literature will converge to the local optimum with varying degree of efficiency, although even this is not guaranteed. If one starts the iteration too far from the local optimum, the some insight is therefore usually required to find the suitable starting point for the iteration. Offer past experience can serve as a guide. So following are the four cited optimization case study along with their application used for induction motor design. So coming to first case study, induction motor design using nonlinear programming as a boundary researcher along with the active constraint. The concept of here is that the because of the constraint, your optimum design will be always on the boundary. So the optimization of induction motion design usually formulated as a nonlinear programming problem as find the x dash, that is the variables where the variables are greater than 0. They have some, because variables are normally taken as a dimensions or some variable which are not, which are non-zero, and most of the time in this machine positive. And then calculate the typically your objective function C as a function of k1x, which is minimum or maximum. Take for example, material cost should be minimum or efficiency should be maximum. So depends what objective function you are taking. And then you have a constraint which is the constraint of nature less than 0. With the inequality constraint or equal to 0, which are equality constraint. Like, so you have it, most of the time where objective function, where inequality constraint, equality are real value, scalar value, and k dash is the constant parameter and x dash is the n variable for which the optimization is performed. The functions, objective function C as a function of k1, a specific set of constant parameter and n variables is called objective function, for which the optimum value of x dash result is typically the minimum or maximum of objective function value. Usually the objective function may be identified within the production cost or annual cost, capitalized cost, efficiency, weight or volume of the motor, and performance procedure of motor additional requirement and dimensioning limits are referred as a constraint and can be of two types, like inequality or equality constraint. Now, case history 1, this is nonlinear programming boundary structure. So, solving the constraint optimization problem may be classified into two categories: search method that solve the constraint, that optimization problem directly, we call it direct search method, and search method that first transform the constraint optimization problem into unconstrained optimization and then make use of the unconstrained optimization method to achieve the solution. Because the unconstrained optimization method, mathematically they are available, quite a lot. So, these above methods are again divided into interior and exterior method, because your design will be certainly on the boundary. So, you can approach to the optimum design either from interior side of the design with the feasible design, or you can go from exterior side feasible design on that boundary. So, method described in this example is the boundary search along with the active constraint method, and typical example you can have a how the global and how the local feasible design comes here as optimum design. So, in this case the objective function is taken as a polynomial of the variables, typically of xj, where the xj real valued scalar function of n variable and is the sum of pre-product, and exponential bj are the real numbers, positive and negative, and the coefficient ai are the positive. This type of function is called polynomial function and has the property of having a single minimum in the non-negative region of the n-dimensional space defined by typically the variables values. So, typically example here is about, in general, the minimization of material or maximization of efficiency or other parameter problem may be decomposed into the sequence of sub-optimization problem as a number of problems as iterative, and the ym is a set of real value coordination variable and then consists of all the constant value of variable except those as a variables are being optimized, and each of sub-optimum problem is defined, and an iteration is set to be completed when each of the sub has a sequential optimized, and computational is halted when the iteration is complete, either iteration is completed or no improvement in the cost or objective function is seen over the previous cycle. And typical example here how it is a unidirectional approach goes, how typically optimization from iterative process goes, and how the typically the incorporation of design into the optimize. So, this is mathematical of the optimization, nonlinear optimization technique used for but you have to consider all the constraint of practical design of this machine, that computer may not be knowing what is your really practical problems like. So, now coming to typical example, first example as objective function. So, you can have a maximize the motor efficiency, which is very much desired in most of the cases. Maximize the motor efficiency is equivalent to minimizing the motor losses, and since the motor losses are the sum of the individual loss component, so this sum is the polynomial function. So, motor losses consist of stator and rotor ohmic loss, whole loss including surface and pulsation losses in the stator and rotary, friction and windage losses, straight load losses, and the objective function comes 1 minus efficiency equal to P upon PCO upon P1, where P1 is the input power, PO is the no load losses, PC ohmic losses, and eta is the motor efficiency. So, you can typically take this as a kind of minimization. So, now because sometimes you go to minimization, the 1 minus efficiency will be corresponding to the minimization. Now, coming to the another objective function one can choose is like a production cost. The production cost of the motor is a manufacture cost and comprise of active and construction material including the fixed cost. The active material cost include the laminated core and the current conduction material of the stator and rotor, and construction material include the frame and valves, shaft, etc. The cost of all material include their processing cost. The fixed cost is independent of the motor design and certain range of the power rating, and therefore the equation for production cost is equal to Cm plus Co, where Cm is the your cost of process material, C0 is the fixed cost, and Cf is the cost of process construction material. So, this comes total Cf plus Cfe plus Cu1 plus Ce2 plus C0. So, where the Cfe is the cost of process electrical steel, Cu is the cost of process stator copper, and Cu is the cost of process rotor copper, maybe aluminum or copper. Coming to annual cost, this is sometimes taken as another objective function or as a part of objective function with the hybrid objective function with proper weight. The annual consumer cost include the acquisition of cost of motor and is related to the cost of process active and construction material like Cm, the cost of annual cost Cl, and the fixed cost Co, and Cn will be R upon 100, CO plus C0 plus CL, where R is the fixed interest rate on the capital investment and CL equal to W into 2 PO plus PL, where W is the energy cost in dollar per kilowatt hour and the T is the annual operating time in the hours. Like now coming to capitalized cost, the capitalized cost function is obtained by converting energy cost from annual cost, dollar per kilowatt hour into year, to investment cost dollar per kilowatt, which is added to the production cost of the model. So C cap will be equal to CM plus C investment bracket PO plus M PCU C0, where C in is the investment cost factor of the losses in your dollar per kilowatt and M is the motor load factor. So here we have a some of the parameters or variables we consider, like a stator bore diameter for induction motor, stack length, volumeter is core length, and height of the stator slot, mean width of the stator slot, height of the rotor slot, mean width of the rotor slot, height of the stator back iron, maximum air gap flux density, then the current density of the stator winding, current density of rotor winding. These are the some of the variables people have considered in the past 4 of this induction motor design optimization. Now, the standard requirement or constraint for 3-phase Skulking induction motor, which people have considered, are important, like power factor at rated load, rated power factor, log rotor current or starting current at to current rated current ratio, starting torque to rated torque, breakdown torque to rated torque, efficiency at rated load, full load slip, and temperature rise according to insulation normally for the winding. And these are the typically you can see how production cost functions of the motor and all the constraint. They are very, so you get very small space with the constraint optimization to get final design as you look into the parameters, and similarly for efficiency. So here it is a production, first is the production cost, how the boundary comes finally, and second is the case with the typically the efficiency and production cost function in the DL plane, like stack length and this you can call it diameter and stack length functions, like as a typically with the sensitivity analysis. And these are the typical sensitivity analysis for different materials, how the typically maximum efficiency can be achieved, as well as the cost with the different kind of material. Similarly, you can just see how the effect of the production cost on the maximum efficiency. So how the efficiency you increase, the cost of production cost is also increases, and cost of increase on the efficiency. So efficiency change with the cost increase, like what is the difference like. So as you are seeing in general, when you want to increase the efficiency, cost also increases of the motor, like. And these are the sensitivity analysis for 1 to different parameters, like how the main dimensions and flux density changes with the efficiency. The all sensitivity done for all the dimensions or all these parameters or variables with the with the efficiency also in case of like a power factor versus efficiency also with the cost constraints, like. So the different exposure by efficiency and power factor with respect to the voltage, how it changes, and how with the load your temperature rise as well as the efficiency and power factor changes. So these are the typical sensitivity characteristics, like temperature rise, how it changes with the load as well as power factor, efficiency are changes. You presume that the load increases, obviously power factor improve, efficiency also improve, and temperature rise also increases. Similarly, as how the efficiency get affected by the cost, like for different kind of steel, like also. And then typically you can see the efficiency and cost increases with the typical cost of investment cost, like. So all these sensitivity analysis are done virtually for the design of this induction machine as an example. Now coming to second case study in design using the constraint Rosenbach method, which is a direct search method invented by Rosenbach as a Hayes algorithm. So example is like as a problem formulation. In the present history, the optimum of multivariable nonlinear function subject to nonlinear inequality constraint is determined, and mathematically the problem can be put as a optimized objective function f, which is a function of all the variables x1, x2 up to xn, and subject to the constraint of LCK, typically as a boundary of the variables as well as the constraint on the performance. So implicit constraints are the dependent functions on the explicit independent variables, and the upper and lower constraints are the either constraint or function of independent variable. As you can see from the example here, how the constraints are. So the method is the procedure based on automatic method, that's a synthesis approach proposed by Rosenbach. It is essentially a sequential search or direct search method and proved to be effective in solving the problem where the variables are constrained and associated with each pair of constraint in the second equation. Rosenbach defines a boundary of region during which one can make a iterative procedure of within the boundary, as you can see in the by couple of these relations. The procedure requires the starting point that satisfies the constraint and does not lie in the boundary zone. An algorithm proceeds as a starting point, initial final step size of the variable, and then define the typically f0 and the current best objective function for the point where the constraints are satisfied, and f is the current function for the point where the constraints are satisfied, in addition to the boundary not violated in those cases. Then the method algorithm proceeds as follows. The first variable is stepped as a distance e1 parallel to the axis, and then function then the current value objective function evaluated, and the worst for these constraints are valid. Then there is a failure and e1 decrease. So you just change, you really deaccelerate the variables with the factor of beta, and you accelerate the variables by factor of alpha. And here the alpha and beta usually are taken 3 and 5, which Rosenberg proven in his example of 1962 paper of computer journal. Like, so coming to the fourth current point, to find typically objective function f nu equal to f fold minus f dash as a function of this, where lambda is distance between boundary zone or so. So if improvement in the objective function has been obtained without violating the boundary zone or constraint, f is set to the initial design for the next initial, you can call it as a accepted design for the next iteration, and next variable is the stepped again in the parallel to axis, and same acceleration, the acceleration of reverse process is followed for all the variables in consecutive repeating sequence until a success and failure has been encountered in all the n directions for all these variables. Like, so then the axis and then rotates, each rotation comes as a stage. The following equations are used for that, typically the relations, and where these are the all parameters defined. The search is made again for the x directions using the coordinates with the xi old plus ej mij. So program is terminated if the number of stage prescribed exceeds the prescribed limit change or in the objective function or vector component is small enough without not giving much improvement in the objective function. And this is typically you can call it the flowchart of constraint Rosenberg method, starting from initial, then you calculate the implicit explicit variables and evaluate the function, then check the boundaries and get the typically whether it is improving or not improving. Then you have to go with the acceleration or deacceleration factor for defining all the variables in sequence for this design. So now coming to typically the objective, the cost of active material has been considered as the objective function, and then the consist of copper of stator and rotor lamination, cost of and rotor run, and constraints have been like a maximum stator flux density, usually 2 Tesla, stator temperature rise 70 degrees Celsius. It depends on the type of insulation. Then full load efficiency, typically no load current, typically 0.5 per unit as a function of rated current. Then starting torque around 1.5 per unit. Then the maximum torque not less than 2 per unit, slip not more than 0.5% or 0.05 in per unit, full load power factor not less than 0.8, and temperature rise not more than 70 degrees Celsius. So variables can which are considered this example, like ampere electrical loading, ampere conductor per meter, ratio of stack length to pole pitch ratio, and ratio of step to width ratio, slot core length L, and average air gap flux density, and stator and current widening current density. And these variables, of course, 7 variables are taken here as a for it. And of course, the result of optimal design obtained for a higher stator current density than the normal use, and for class of insulation considered class B, and with the constraint of temperature rise and high value can be justified, since winding current density alone is not possible for the temperature rise, but it also depends on product of ampere conductor per meter and winding current density. And use of higher current density reduces the stator slot size, and hence the maximum teeth flux density is also reduced, so the no load current, and high value of stator current density increases the stator resistance and temperature, and giving a rise in the motor copper losses. This decreases the efficiency of motor, but at the same time power factor and torque are improved. So there are a lot of contradictory comments. The major cause of reducing the cost of is less with the winding copper. So coming to the third case history is a sequential and constraint minimization technique in conjunction with the Rosenberg method of direct search. So what we do here, we convert this constraint optimization problem by this sequential and constraint minimization problem by suitable modification, and then use unconstrained minimization problem by using a direct search method of Rosenberg. So in this process, we use virtually, you can call it the design what we got best, we consider initial design for the next set of iteration. So we presume that it goes to the global optimum or conditional optimum, the best design typically. So here we say find the typically a set of variables where the objective function may be minimum, like a cost is minimum or efficiency is maximum, and subject to the constraint, I mean typically m constraint, and with the variable limits, I mean independent variable limit, because these are the practical parameters so for the n variables. So you have to find out the set of independent variables and their lower bound, the lower limit. So fx is the objective to be optimized. Like, so here what we do it in the present study, the following 9 design variables are considered, like a stator stack length, then average air flux density, ampere conductor, electrical specific loading, stator winding current density, rotor winding current density, stator core depth, air gap length, stator slot to width ratio, rotor slot to width ratio, and remaining design parameters are expressed in terms of these variables assigned as or fixed design variable. And considering the objective, fx is the objective function to be optimized. It may be either performance oriented based or some form of cost consideration. In the present case, following 6 objective functions are considered. The first objective considered is the manufacturing cost as the cost of active material, consisting of stator rotor laminations and winding material, and cost of iron for stampings and the winding material, and cost of iron and stamping considered the rupees 20 per kg, and copper with winding material as a both operator, and cost 60 rupee per kg. So you consider from every point of manufacture. The second objective function is considered as the cost of annual energy consumed for 20, I mean operating hours of 2500 operating hour at the energy cost 0.2 per kilowatt hour is considered from the viewpoint of consumer on account of increasing cost of electrical energy. And third objective function is certain part of cost of material and operating cost of in consider of 20% of active material cost, and typically for the annual payment based on the capital cost such as insurance, interest and replacement, plus the sum of annual. Most of this is done in advantage of consumer as well as the system economy. Fourth objective function is taken as a full load power factor, which is to be maximized. This considers the some of the application operating power factor found to be poor, quoted by supplier of energy. There is also effect of some saving in investment required for improvement of power factor. The analogy may be applied for typically maximizing the power factor for any operating. So fifth objective function is taken consider as the annual operating cost on the basis of kVA input. An annual kVH cost is taken as a 425,000 hour at the cost of 0.25 kilowatt kVH. This is done from the viewpoint of supplier as well as utility concern. The sixth objective and last objective function includes certain part of active material cost plus the annual kVH cost of the motor. It consists 20% of the active material cost, and annual payment based on the cost of insurance is placed on, plus the sum of annual cost of kVH consumed by the motor, and this is favorable for utility concern as well as the overall economy of the system. And of course, constraints are typically the maximum stator flux density less than 2 Tesla, rotor flux density less than maximum torque and not less than 2 per unit, starting torque more than 1 per unit, starting current less than 5.5 per unit, full load slip not more than 5.5%, full load power factor not less than 0.8, full load efficiency not less than 0.8, and no load current in per unit not less more than 0.5, and stator temperature not more than 70 degrees Celsius. So along with these performance constraints, the side constraint, lower and upper bounds of variables are also imposed to obtain the feasible design. In the evaluation of objective function fx and the constraint gjx are as well as the calculating the performance of index motor, the extended mathematical formulation and normal material properties are used. So here is the process sequential unconstrained minimization technique. So design optimization of index motor, which is highly nonlinear constraint multivariable optimization problem, may be solved using either direct or indirect search method. And here indirect search method, namely sequential unconstrained minimization, in short we can call it SUMT, in conjunction with Rosenberg method of direct search for such type of problem, has been employed in the design optimization of typically of this. So in SUMT, the constraint optimization converted into series of unconstrained problem, typical example with penalty term. So we have a P equal to, we call it augmented objective function as a cost, original objective function with the constraint on the boundary like Rk j to 1 to m 1 upon Gj, where Pk is known as a augmented objective function, sigma term called the penalty term is to ensure the feasibility during the minimization process. In the scalar, Rk is called the penalty parameter or factor, and Gj is the normalized form of all the constraint in such manner they lie within the -1 to 0. And this is the typically the flow chart of this. Read the Reiterating initial design, step size, boundary of constraint, characteristic data. Starting from K, formulate the augmented objective function PR. Find the unconstrained minimum of this. Is convergence obtained? Yes, print the optimum design. If no, then you have to change the typically penalty factor and go to iterative manner. So the process started with initial feasible design and then design of verifying the all constraint. The starting value RK is coordinated, so the starting value of PK is high compared to Fx to get the quick convergence of the process. Then the augmented objective function is minimized with the help of suitable unconstrained management technique, and presently here taken Rosenberg method without any constraint to get the point Xk. So now the augmented objective function is formed with a modified penalty factor Rk equal to less than Rk, where Rk is C, where C is less between 0 and 1, and again minimized with k plus 1. In this process, the unconstrained minimization before decreasing frequency of value of Rk that is necessary to propose convergence criteria to identify the optimum problem. So convergence criteria is that the process continue either for predetermined number of iterations until the process objective function becomes less than a specified small quantity. And these are the typically you can call it optimization of 3.7 kilowatt 400 volt 50 Hz 4 pole motor with the different you can call it objective function 6 objective function which we define. So the value of the variables, then value of the constraints, and then value of the objective function. So you will find in all these design with the star the objective function value is typically the minimum or maximum corresponding to different designs like. So coming to the case study for design optimization of small 3-phase induction motor using incremental search method. Here what is done as a starting process, the mass production of relatively small motor generally require the many quantity which can be varied with the production of a small typically numbers of large machine must be held. So in case of a small motor, the frame size, lamination, stator and rotor assembly and the winding layout is standardized. Thus the only variables are the number of turns per coil and wire diameter and typically stack length. So here of course it is given an example in this publication. So what they have considered the optimization used incremental search will in problem main nonlinearity involved. So design specification is like operating voltage, number of poles, full load, output power, maximum power factor, and typically the temperature rise, minimum value output, and the maximum value of stir. And objective is the aim of optimization procedure to meet the above specification minimum material cost. So here the effect of design variables on the sensitivity analysis, typically how really it affects the temperature rise. So stack length and wire diameter are selected, then the full load current and the corresponding winding temperature may be obtained for any value of turns per coil, and the full load temperature rise with respect to the changes value zone. So and now stack length is allowed to vary how the typically the temperature changes with the turns per coil. And similarly you see the sensitivity analysis corresponding to varying the stack length. As you see the stack length with the typically different stack length how it is changing. Typically the you can call it the temperature rise with turns per coil for different value. So you can see not more than 3-dimensional value here. So effect of for each diameter, each wire diameter there is a minimum temperature rise, and that's smaller the wire diameter, higher the more pronounced minimum. So linear line representing the maximum permissible temperature and the maximum permissible slot factor listed design are shown superimposed in the figure. So and similarly these are the sensitivity analysis virtually of these all 3 parameters, and then this is the selection of optimized you can design. So selection of optimum design, if the temperature characteristic for particular stack length and particular output are considered, it will be seen the characteristic correspond to smallest wire diameter to produce the winding within the design area. And since reducing the number of turns per coil of a given increases the maximum or starting torque and reduces the material cost, the winding corresponding to O1 is here the obvious choice for that particular diameter. So now further, if winding O1 meets the torque specification, then winding O3 will all meet the torque specification, since the increasing the wire diameter, reducing the number of turns per coil, increasing the maximum and starting torque. So if the winding which meets the torque specification are selected O1, O2, O3, and then optimum winding for that stack and the output can be selected by costing. So then repeating the procedure in another stack may produce the more economical combination of the stack length and winding and plotted the per unit material cost versus stack length, and result indicate that the, for example, consider a small reduction in cost will achieve the useful non standard stack length. So when material cost of several standard motors were compared with the optimized equivalent, it was found that the material cost reduction is up to 14% were possible in this process. Now coming to as a tutorial as a computer program for performance prediction. As studied previously, the one of the primary usage of the computer is in problem due to the ability of automate a large number of repetitive process or subroutine to obtain the large set of design output data. An example of 3 repetitive discrete steps in design will be, for example, prediction of parameter 1, say output performance, with respect to the change in parameter to input variable for a wide range of the parameters. So here you can just see how the torque and speed changes with the, typically you can call it with the with the current density, and similarly in second case how the copper loss and active material cost changes with the. So two example, the optimized results or so on. Now coming to example 1, develop a computer program to compute torque process characteristic of a 3-phase induction motor at rated voltage and frequency using equivalent circuit data from slip varying 2 to 1. What happens if the rotor resistance changes? You can see perform the design of induction with given specification, assess the no load and full load performance, note the typically the induction motor equivalent stator resistance, stator leakage reactance, rotor leakage, magnetizing reactance. Now we can need to assess the variation of rotor resistance R2 on the torque and also to be considered form. So you can see how often results are shown in these characteristics like. And now typically here a motor data are given like a 415 40 kilowatt 4 pole on rotor induction motor data are equivalent circuit data are given, and you from this you can find out typically the performance like equivalent impedance from parameters and then the Thevenin equivalent, and then you can go ahead all the calculations. Similarly, then you can go for speed calculation, then the current terminal current, then the mechanical torque like calculation, and this is typically how you can put as a program code for calculation of in MATLAB, which is a very simplified nowadays. You can do very quickly the repetitive calculation for these motors. Similarly, the calculation of all the parameters and these characteristics. So similarly, we have some other examples. So develop the algorithm for computer to torque speed characteristic, voltage versus speed, power factor versus speed, and develop the algorithm for computer to compute the speed characteristic, output power all characteristic from varying virtually the output power from 5% to 150%. Develop the algorithm to calculate air gap, record and record teeth plug density, their value, weight and no load, and then the equivalent your shunt branch equivalent parameter of 3-phase at varying voltage from 5% to 150 with the increment of 5% and considering the diameter. Similar example, develop an algorithm with the computer program to calculate the block rotor parameters if dimensions are given and material property. Similarly, algorithm you can just calculate the performance like starting current plug if your parameters of equivalent circuit are given. Similarly, you can develop the weight calculation, loss calculation if all parameters are given. So now coming to the objective questions, the air gap of the 3-phase induction motor is kept small in order to reduce the magnetizing current. If the leakage reactance per phase of state of 3-phase induction 10 and the turns per phase increase 10, the leakage reactance will be 1.1 square. So you have a lot of objective questions which you can go through. Like in these typical examples like around typically a kind of 50 examples for a short example. So now coming to subjective objective. So which gauge of double cage induction motor is effective during starting? Upper gauge induction motor is effective during starting. What type of starter is used for starting of induction motor? The rotor resistance starter can be used to calculate as the rotor terminals are not accessible. Only how can an induction motor be designed such that it has the best performance for obtaining the T is taken under root 0.18 L, where the mass finding is used. The mass finding is used in small motors of less than 5 horsepower. There the maximum torque produced in induction motor and the rotor is equal to the total. Mention the most important consideration determine the election of air. The most important consideration is determine the length of air gap in the induction motor power factor. How does it increase the air gap affect the motor? Increase air gap causes higher magnetizing current, better lower power factor and higher overload capacity. What is the stator of 3-phase induction motor laminated? Lamination is usually done in stator teeth and stator core to decrease the iron loss or radicant loss in that. Why the stator cores are made of segmented lamination for large size, as it is wasteful material to have single large size stamping punch on the wire. Mention the various type of winding employed in the rotor. The different type of winding is induction motor, the rotor or mesh winding or double layer bar winding. How can the crawling can be prevented? And the effect of crawling can be considered reducing the output by suitable choice of standard slot. Mention the region of zero harmonic leakage again in the skull cage motor rotor current balances the current on account of harmonic flux is zero. Mention the appropriate range of the rotor frequency in this. The range of frequency of three-phase induction varies from 1.5 to 2 Hz at full load. What is the overload capacity of induction motor decreases with increase in the electrical loading leads to large turns per phase, hence leads to. So reduces the circle diagram and lower. So similarly, the induction machine is small air gap. What is the percentage of unbalanced magnet pull becomes high as a small air gap? If the rotor is out of center or is centricity there by the small amount. How the increased value of a specific loading affect the cost of machine. From the output equation, it is observed that the increased loading, volume of material decreases, so hence the size and cost are reduced. What is the minimum value of the slot pitch for them? The minimum value of slot pitch is the 15 because of mechanical constraint. Name the material used for insulation and material used for insulating the core and are kaolin and varnish. What is the why the short coated winding are used in induction motor? Short coated winding use the length of the main turn will lesser than that of full pitch. This is called of course reduction. Similar use of short coated winding element is a certain harmonic pole. What type of slot provide the quieter operation? The closed or semi-closed slot provide the closed. Which type of frames totally enclosed? The frame are totally enclosed are provided with the axial fins as they increase the surface area and make the cooling effect. What is the delta connection usually preferred in three phase? The stator of which skull ground is normally connected to delta as it allows the star delta starter use of star delta starter which is cheaper. What type of construction of three phase slip ring motor? The slip ring motor has a two major parts, and rotor. The stator has a core and winding and which are and rotor consists of core and winding. What type of specific features of skull cage rotor? The cage rotor has can be used by varying the number of edge and poles. All the starting method can accept the rotor resistance starting can be used. Is resulting construction cheaper and rotor overhang leakage reactance is reduced, resulting in better power factor, greater pull out torque and overload weight. Why does the slow speed induction motor have a inherently poor power factor? The slow speed induction motor have a large number of poles. So it requires increased magnetizing current, which ultimately leads to inherent power. How can a complete performance of design motor can be found graphically? Circle diagram can provide the basic rotor and circuit and can be used for complete the calculation graph. Why the die cast aluminum bar more commonly preferred to use in comparison to copper bar? Die cast aluminum bar are more commonly used in comparison to copper bar as it reduces the cost and make the mass production easier. How can the tooth as well as cost is low? So how tooth pulsation loss can be reduced in induction? The tooth pulsation loss are proportional in number of waves. The minimum variation in their gap reluctance is possible use of large number of narrow slope. So specify the range of specific magnetic loading, electrical loading. Specific loading varies from 0.3 to 1 Tesla and specific electrical 5,000 to 45,000 ampere. Provide the thickness of lamination generally used. The lamination used thickness 0.35 to 0.5 millimeter. And these are the some of the references from which we have taken this lecture material. And thank you very much.